Hello, everyone, and welcome to today's webinar, Multi-Cloud, One Command with Terraform. Today, you will hear from Mitchell Hashimoto, the creator of HashiCorp Terraform, and Calvin French-Owen, the co-founder of Segment. Segment is a Terraform customer that has perfected their blueprint for provisioning cloud infrastructure that optimizes resource utilization while controlling costs. Please feel free to type your questions during the webinar. We will compile all questions and answers at the end of the webinar and send the results to everyone who registered. This webinar is recorded, and the recording will be made available after post-processing, usually within about 2 days. With that, let's go ahead and get started.
All right. Hello? All right, there we go. Hello, everyone. Let's go ahead and get started. I'm going to be talking about Terraform today. As a quick introduction, my name's Mitchell Hashimoto. I'm one of the co-founders of HashiCorp and also one of the creators of Terraform as well. And so spent a long time with Terraform, and there's been a lot of exciting changes recently. Excited to share those with you. But also going to spend some time talking about just introducing Terraform today and its usage. So here's a basic agenda of what I'm going to be talking about today. I'm going to start with talking very briefly about HashiCorp in general. We make a lot of tools, and while those aren't the topic of today's webinar, people usually are interested in how one specific tool fits into what we're doing. And today that's Terraform, so I do want to talk about how Terraform fits into the HashiCorp product suite. Following that, I'll go over use cases and sort of the problem statements that Terraform is trying to address, followed by a fairly brief, probably 10 to 15-minute introduction to Terraform. For those that know it, it'll be repeat knowledge, but there's generally a lot of people on webinars that are new to the project too, so I don't want to dive just directly into new features. And then I'm going to finish it off with about half an hour of new features in Terraform 0.8 and 0.9, which are two recent major releases we've had in the past few months. So let's go ahead and get started. So this is a diagram we use to sort of describe what HashiCorp as a company tries to achieve. Our goal is to enable companies to provision, secure, and run any infrastructure for any application. And sort of our worldview for that is splitting things into these three layers here. The layers are run, secure, and provision. And we build products that generally fall into these three categories. So in provision, we have Vagrant Packer and Terraform, and these are concerned with setting up the infrastructure and changing the infrastructure over time to support applications on top of it. Above that is a security layer. All security for us is done through Vault. And then above that is where you run your applications. And we have Nomad for that, as well as Console to do service discovery and connect everything together. This is how we like to break things down, since having a model like this is super important in understanding, how things interact with each other. Like, for example, today I'll talk a little bit about Terraform's integration with Nomad, which was new in 0.8, but we also have integration with Kubernetes coming in right now in 0.9, and you could see, like, through a diagram like this, the Terraform and Nomad, Terraform and Kubernetes are completely complementary. It helps sort of split that up and see what works with each other and what may overlap instead. So Terraform for us is solving, has a few major use cases that it's trying to address. So one is infrastructure as code, being able to describe your infrastructure using text, using code. And this is just super important to better automate things, better keep track of history, better work in a team environment. There's just a lot of tooling out there that makes working with text really efficient, and it's just a lot better from an efficiency standpoint than clicking on UIs. Hybrid cloud management. Terraform is about about 3.5 years old now, and we sort of recognized that when we were creating Terraform, there was a few cloud-specific tools that did what Terraform is doing, but there wasn't any really that did it for any cloud platform or multiple different what we call providers, and we felt that was going to be an increasingly important thing. And today, that seems to be the case. Most organizations we talk to today have some form of hybrid cloud happening, whether that's just multiple public cloud providers, public and a private cloud. There's something happening there, and having one tool to be able to describe all those things is extremely important. And then the last thing is self-serve infrastructure, and this aligns with sort of our view on DevOps, and what we like to define as DevOps, which is trying to enable teams to work efficiently in parallel in order to get an application out quickly while being safe. And infrastructure could be seen at times as a bottleneck to that. If a developer wants to make changes to an application or also to infrastructure, having to go through one central location can often be a bottleneck. And one of the things we're trying to achieve with Terraform is to enable everyone to self-serve portions of the infrastructure, and how that's done is still managed, by a smaller set of teams, but at least it gives them a safe boundary with which they could do it. And so where Terraform fits here in the ideal workflow that we were trying to design was you have a bunch of people working in parallel on their own teams, collaborating on infrastructure as code using typical methods. Treat your infrastructure like you would an application. You pull requests to make changes. You review the code. You run tests in a continuous integration environment, and then you merge and apply. After that, you do validate, which is that testing aspect, which is the review process, and then finally you just let Terraform automate the change and make the change go out. And this should work for, like I said, multiple cloud providers, because once you have that, then you have this one single workflow that applies to any sort of infrastructure change you're trying to make. Okay, so that was really brief on HashiCorp and the use cases of Terraform. And then next, what I want to do is actually just give a really quick introduction to Terraform here. Probably 10 or 15 minutes if you're not familiar with it, or if you're just interested in hearing sort of the core philosophy behind Terraform as a tool. So the goals of Terraform, and these were actually, I pulled this slide word for word. It's a new design, but I pulled this slide word for word from a deck I had in 2014, which is 3 years ago, because the goals of Terraform just haven't changed, and they've withstood so far the test of time over those few years. So the goals of Terraform when we initially created it and to this day are to give a unified view of your infrastructure. So I wanted to solve this problem where when you join a company at the time when you joined a company as an operator or someone working on infrastructure, it almost felt like the way you got the lay of the land was this oral tradition, this practice of talking to people that have been there longer than you, figuring out what they know, but then someone else knows something a little bit different, and merging all this knowledge together before you have some view of things. And what I wanted to get to was basically you join, you don't have to talk to a person, they point to the code and say, that's the source of truth. That is our infrastructure. And you could just learn from there. The next one was infrastructure as code. So again, I've hit this a few times, but just being able to describe things using text is so important for collaboration. It's hard to collaborate across the hallway, let alone across the country or the world when you're clicking on UI elements. It's a lot easier when you can diff things and see changes in text. Composing multiple tiers. So this is actually how we describe multi-cloud as well. So maybe this text is the only one that I would change slightly, but it's still true here too, which is we wanted to do multi-cloud, but in multiple cloud, it's really multi-provider because we wanted to do different layers as well. So we wanted you to, for example, spin up your infrastructure on a provider like Amazon Web Services and then after that, install something like Nomad on top of it, and then after that, deploy applications onto Nomad. And those are 2 or 3 different levels of abstraction there, and we wanted that to all happen in one Terraform command if possible. So you'll see some examples of that very shortly. We also wanted Terraform to be able to change infrastructure over time. There were tools around the creation of Terraform that were not bad tools for bootstrapping infrastructure as code. You could describe your infrastructure, spin it up. Some claim to be able to change infrastructure over time, but the general feeling I had at the time was that these tools were dangerous, or they felt untrustworthy, even if they worked. They were scary, like they were, and I'll explain that more when we get to how Terraform addresses that. And then the last thing is just one workflow. Learned from earlier tools we made that there's so much power in having one workflow to do things for all your environments. And we wanted Terraform to do that, whether you're using AWS or Azure or Google or Oracle or anything else. Like, we wanted to make sure that you only had to educate people on one workflow and have it scale across all those things. Okay, so those were the goals, and those were inception goals, and they're still valid today. The way we achieve those goals are features, and the features, these are the core fundamental features of Terraform. These are things that haven't changed in a long time, that continue to improve and get changes in that way, but they're not sort of like the features I'm going to talk about in 0.8 and 0.9. These are like fundamental. Terraform isn't Terraform without these things. And so the first feature is open source, and I consider this a major feature of the tool. And so here's like something I grabbed from the Terraform GitHub a couple days ago. And the important highlights I like to pull out are these 3. One, there's like the superficial metric of stars. It doesn't really mean anything, but the nice thing about stars is that they are a decent barometer for community interest. Something that has 1,000 stars versus something that has 1 generally means that it's being looked at by more people, and that's what I extract from that. The next super important thing is this contributor count. 950 contributors over 72 releases. This is a big community, and it's a very, very active open source project. These contributors are basically the key to making Terraform tick as well as it does, because one of the most common pieces of criticism we got when we started Terraform was doubt that a project that we were doing could keep up with, say, AWS and CloudFormation as an example, but more generally could keep up with the cloud provider native tool. And we've shown over the years that not only can we keep up, we very often, I mean, multiple dozens of times now, we've beat them to supporting their own features. And it's not every time, but it has happened multiple times, and it's due to these contributors. A lot of times an announcement will be made, actual like HashiCorp employees may be busy working on something else, but within half an hour, there's a pull request to implement that feature. So the open source aspect of Terraform is extremely powerful. And then as an asterisk we do have a Terraform Enterprise. It is a commercial closed source application, and I'm going to talk about it a little bit, but it's built on top of Terraform, so it's not Terraform itself. Yep, I mentioned this. The one metric here, which is really interesting, is I just looked for this past week, and in the past week, we had 42 contributors push 263 commits. So that just shows some of the velocity just even this week. Okay, the next major thing is infrastructure as code. This is, I find, best as an example. So here's an actual example of Terraform configuration. Spinning up a Google compute instance and then creating a DNS simple record to point to that instance that it spun up. You can see it's just text. It's line-based. You could diff it really nice. It integrates really well with version control. And this is our human-readable format we call HCL, but it's also JSON compatible. So you could just write JSON too if you don't want to learn a new DSL. This thing I highlighted at the top is what we call a resource. It describes one thing that Terraform manages the lifecycle This is an instance, a load balancer, a DNS record, a GitHub repository. It's a noun basically. And then this other thing I highlight down here is a way to connect things together. So this is referencing actually a parameter, a result of the Google Compute instance. So it's getting the IP address to set up the DNS record. And this shows how you could glue together completely different providers. Like Google, it's highly unlikely, for example, that Google would ever provide a tool to manage DNS simple records. But it completely makes sense in the context of Terraform. And so a lot of this stuff I've already said, but one aspect is that it's declarative. That's super important. You don't explain to Terraform how to do things. You just explain what you want, and it gets you there. And that makes it much easier to scale to large infrastructures where the how becomes very, very convoluted. And you could split this up into multiple files and modules. So just like how you would organize an application, if you're programming an application, having infrastructure as code gives you the ability to organize your code in various ways. So files are obvious, and modules are a way to, they're basically a folder of Terraform configurations that are reusable, that people could reference. And so there are reusable encapsulated component of Terraform for shipping around behavior. And that's one of the key ways, for example, that a central IT type organization can allow others to safely modify infrastructure because maybe they're curating the official set of modules that other people could use. So that's one way that happens. The next thing is resource providers. Resource providers are what are the integration point for Terraform. So this is the point where Terraform can integrate with other vendors, cloud providers, and other things. They expose resources, hence they're called resource providers. And these resources are specific things like an AWS instance or security group or load balancer. And implementing these is super easy. You just basically have to tell Terraform how to create, read, update, and delete a thing. And then Terraform handles all the other aspects for you. And the ease of implementation is one of the key parts of Terraform's growth. It's what enables a new cloud feature to be implemented by a community member who's not full-time on the project, in less than half an hour. Being able to easily add things is really critical. Here's a list of some providers. This is a list of around 25 or so. Terraform actually today has over 75 different providers, so there's a lot of things that Terraform can control. But there's a few sets of categories here which are interesting to call out. So these highlighted ones now, these are cloud providers, infrastructure providers. And so, this is an obvious use case of Terraform. Terraform spins up infrastructure. I've said that sort of multiple times. But you can see there's a lot of them, and then you can see there's a lot of stuff that aren't infrastructure providers that Terraform can control. So this next one that we highlighted, these are DNS providers and CDNs. And so that becomes a little more interesting, a little less clear of how Terraform does that. But an easy example is you spin up a set of AWS web servers, and then you configure Fastly as a CDN in order to front those. Or you don't spin up servers at all. You're actually just using Terraform's infrastructure as code to manage your Fastly configurations. And I'm calling out Fastly in particular just because they actually have a really good set of blog posts on how to manage your CDN configurations with Terraform. And that's a really interesting thing, even if you don't glue them together. DNS is a little more obvious for how you would connect DNS to things, infrastructure you're spinning up. But there's still more, and these get a little less clear in their usage here. But these are version control systems and monitoring. And one example here is that GitHub, for example, you have to manage organizations and teams, and what teams have access to what repositories, and what repositories do you have. And you could actually manage all of that with Terraform. And so the benefit is you actually have a source of truth of who's on what team and what teams could access what in code that you could collaborate on and apply, and Terraform detects divergence. So you'll see if someone showed up on a team, but they're not part of the infrastructure as code. So there's some fun use cases there. And then the last one here are databases, and then just like different different layers of infrastructure. So Cobbler would be bare metal machines, and Docker would be application containers. And so you could see that Terraform can manage those things as well. All right, plan and apply. So I showed you this this example a little bit earlier, and so then the question becomes, how do you actually make this example happen? How do you run it? The first thing you generally want to do is run a plan. And a plan is the Terraform feature that shows you what will happen. Basically, given the current state of the world and your desired state, which is your configuration, like what will Terraform do to get you there? And that's super important for declarative systems and for infrastructure that scales to a much larger size. When you have a small infrastructure and you add a new server, you generally know just immediately, intuitively what Terraform is going to do. But when you have, let's say, 1,000 resources that are connected to each other in various ways, and you change 3 different things that are maybe related and you're not sure, it's hard to know the actual impact on your infrastructure of that change. And one of the important pieces of impact that Terraform shows you is potentially destructive actions. So every cloud provider and every basically like resource provider has APIs that sometimes require destruction to change something. Like, for example, you can't change the AMI of an Amazon instance without recreating the machine, even if you want to attach, the same disks and the same IP and all that stuff. If you change the AMI, it necessitates a destroy and recreation of that instance. And it's not always clear when that'll happen. Again, for someone familiar with AWS, like changing an AMI may be obvious, but for the full set of things that require destruction, it's not immediately clear. But Terraform shows you that. So you could run a Terraform plan. You see that, oh, this actually requires destruction. That might entail more downtime that I'm comfortable with. And you can modify your desired state to maybe avoid that for now. There's also additional benefits here where, for example, a recent release of Terraform just in the past month made it so that you could resize an AWS instance now without destruction. AWS has supported that for a while. Terraform just didn't do it for a while, but now we do. And so after we shipped that, we got a lot of people on the mailing list in the community saying they were kind of pleasantly surprised that they upgraded Terraform, didn't change anything, and now Terraform's doing more in-place updates. And that's just a benefit you get. A really, really important part of plans is that they're not equivalent to what other software sometimes calls a no-op mode. A lot of software has this idea of a no-op mode, which is just, do it. Act like you're going to do something, but don't actually make the changes happen and show me what you would have done. Plan is similar, except you could save them. So it's a no-op mode until you save it. And once you save it, you could actually feed that saved plan back into Terraform and say, okay, that looked good. Do that plan, but while you're doing it, if anything changes, don't diverge from this plan. And so Terraform will attempt to execute the plan, and if anything changes, it'll cancel the apply. So a Terraform plan looks like this. It's in a diff-like format where it shows you what's going to happen. So in here you can see a plus next to the Google instance, which means it's going to create it new. There's also a tilde for change, in place change. It does a minus plus for destroy and create, a plus minus for create and then destroy. There's all sorts of little symbols there that describe what's going to happen. And when you run it in an actual terminal, it'll be colored too. So creation is green, modifications yellow, any sort of destruction's red. Yeah. So then after you see the apply, after you see the plan, and after the plan looks good, you apply. And apply makes those changes happen. The ordering of Terraform is done based explicitly on the dependencies that you're using, but you don't need to say them separately. So for this example here, the DNS record is very explicitly referencing the Google instance. So we'll do the Google instance first, and then do the DNS simple record. There's also ways to manually specify dependencies. Because we know what depends on what, Terraform parallelizes as much as possible. For cloud providers, this is really helpful because a lot of times, spinning up an instance may take dozens of seconds, and if you could set up other things in parallel, you want to. Doing everything in serial could actually take much, much, much longer. And so Terraform does parallelize work wherever possible. And then finally, it handles and recovers from transient errors. And for infrastructure and API communication in general, this is super important. For just various, real world practical issues, errors happen, and APIs return 500s, or the internet goes down, or the API reports something, but because it's eventually consistent, it's not actually true yet. All these things very regularly happen with all of the most popular cloud service providers out there. And so Terraform has built in a lot of both recovery retry mechanisms, as well as an understanding that it may just not be able to complete, and there might be a partial completion. So if Terraform gets an error in the middle, it does retry a few times. If it doesn't ever come back, it'll return a partial result, and when you run Terraform apply again, it'll just complete the work it hasn't done yet. It doesn't start over from anything. So that's a really important part, because when you're spinning up, especially if you're spinning up a non-trivial infrastructure for the first time, and there's a lot of resources, it's fairly common that a cloud API will fail. Hopefully, Terraform's retry will cause it to succeed, but you just want to have that safety net in case it doesn't. And so when you run the apply, it looks like this. It looks a lot like the plan, except that it actually makes it happen this time. And apply is not only for creation. So apply obviously works for creation, but apply is meant, and this whole plan and apply is made for changes over time. So for complicated changes to your infrastructure, you should still be using Terraform, and just the plan becomes more and more important in order to see what's going to happen. You could, for really complex things, I just highlight here that you could use the target flag to say, yeah, I know I made changes to 10 resources. I really just want to update this one right now. And you could have Terraform just target one change for now. Okay, and then the last just introduction to Terraform aspect I want to talk about is collaboration. Collaboration is extremely important. With configuration just being code, you want to be able to collaborate on it. Infrastructure in general, you want to be able to work as quickly as possible with multiple people, and so it's a key part of it. There's various parts of collaboration built into Terraform, which we consider sort of fundamental safety features of Terraform. But then larger collaboration features, such as remote running, history, ACLs, approvals. Another stuff I'm going to show you is in something we call Terraform Enterprise, which is an application built on top of Terraform, and is our commercial offering of Terraform. So the Terraform open source workflow, which I just showed, looks a lot like this. The reason why we built Enterprise is to avoid this sort of scenario, avoid the scenario where multiple people are trying to modify infrastructure that may overlap. And how do you reason about this? How do you protect yourself against this? How do you see the history of this? And so on. And that's basically the core premise of it. I'm just going to go over a few of its features. So one is remote plan and apply. So you continue to use Terraform as you would expect, except the plan and apply happen in a centralized service. They don't happen on your computer anymore. They happen in a hosted environment. And when I say hosted here, I mean either we could host it, or there's also a private installable version of Terraform Enterprise within your firewall. One of the cool things about this is you could really treat your infrastructure as an application. We integrate with GitHub and other version control providers, so that when you do things like make a pull request, just like when you have a CI like Travis or Jenkins or something, as part of that pull request, we actually run the plan, which again doesn't make any infrastructure change, but sees what would happen if you did. We verify the plan succeeds, and then we show the plan in a link to the plan right in line in your pull request. And then when you merge, it actually makes the infrastructure change happen. So it allows you to just treat this infrastructure directly like an application. And here's just like some screenshots showing what that looks like. So in this case, here's like a pull request that may update an AMI. This is infrastructure code. You could see in the bottom there the checks that passed. You could see that it actually ran plans, and if you hit details next to it, it would show you the plan output, and that would go to this page. So in this page, you could see that we keep a link of where in GitHub this came from, the pull request number and so on. You could click back and forth. And you can see the plan execution below and the output there. So you can see it passed. If the plan failed, it would just be a red X. And then you want someone to come and approve that plan. You want someone to come and say, this looks good, and make the merge happen. Aside for this, one of the benefits of having a service to do this is that you could put sensitive variables directly in the service, and this way the sensitive variables never reach your developer or operator laptops. They still might make the infrastructure changes code. They make a pull request. The remote runner pulls in these variables, but the developer could actually never see the actual value of the variables. So it lets you have these have this partial view of variables and enforce more security that way. Another one of the features is state storage and history. Terraform Enterprise is a location where Terraform can store remote state, and state is how Terraform keeps track of what it's done. It reconciles the state periodically, basically every time you run it with the real world, but it does keep a record of what it's done. And Terraform Enterprise way you could store it remotely. We encrypt it via Vault, provide a way for you to browse the history and changes over time, roll back to a specific state, as well as and lock it to prevent any changes. So here's an example of just a rollback. Obviously, you have to be super careful, but we allow you to roll back if things didn't work properly. The state changes can help trigger notifications of things happening, and we integrate with Console for this. You could go through the history and basically identify who made changes and when. So you could see that maybe it was this change a few minutes ago that made the services go red, and then you act like an application. You make a pull request to make the fix, and do that whole workflow that I just showed you. There's a bunch of, you could revert, make the changes, make the merge, and then you could see the diff of states and basically get back to a passing state. We also have this environment lock, so if you just don't want any infrastructure change to happen at all for some reason for a period of time, there's the big lock button that you could push that makes sure that for this environment, no one's doing any changes until someone manually comes in and unlocks it. And there's various good reasons for that, for maintenance, ongoing maintenance going on. There's an HTTP API, which allows you to do all the things that I just showed via just a REST API. So you're able to set variables, trigger plan and applies, check state history, roll back, look at the diffs, send it to Slack or some other chat system. You're able to do just a bunch of things there. And speaking of chat, yeah, there's notifications. So you could actually register for notifications in these different locations for plans that are going to happen, plans that did happen, plans that erred, plans that didn't work, monitoring checks that failed, and so on. And so you could actually see when this happens. And so that's pretty much the overview of the enterprise offering. One thing I like to answer is what's the difference between open source and enterprise from a I guess philosophical standpoint. So it's important to know that enterprise is an application built on top of Terraform and isn't a modification of Terraform itself. And when you run enterprise, it actually uses bit for bit equivalent Terraform binaries as open source. And actually, you could use multiple. So you could have some Terraform runs using version 0.9.1 and some using 0.8.4. And that's nice because different parts of your company may be at a different stage of Terraform. And the main differentiation is a focus on collaboration, security, and governance of your infrastructure over purely lifecycle management. Okay, so that was the introduction, and now I'm just going to dive right into the new features that we've recently released in 0.8 and 0.9. And this is pretty much just going to be a quick, here's a feature, here's another feature. Some are related, some are not. Here's how you use them. It's going to go by fast, and the point is just to show you the changes that have been coming and whether they'd be useful to you, and just to show you they exist. A lot of times when even if you're using Terraform for years, it's easy to let these releases slip by you and not realize some of the stuff that's in the release you're currently using. And so I want to talk about them. I'm going to start with Terraform 0.8. This was released in December of last year, just prior to the holidays, so easy to miss, and it had quite a few interesting changes in it. So the first one is Terraform console. This is a new command that we released that gives you an interactive environment to basically test configurations, or not test them, but read values from your configurations. So you could read information from the resources you've created. You could run any functions that you could run in your configuration. It's a really nice way to just explore an environment. This is great for obvious reasons, pretty much for beginners. We use it heavily in our training program to get people comfortable with Terraform configurations. And this is a read-only interactive environment, so you can't break anything. It's impossible to change infrastructure from this thing. So it's a really safe space to try things out. It's also scriptable, so you could pipe in scripts to run, and Terraform console will execute them against your current state. This is more aimed at advanced users, and one of the primary use cases I see for this is scripts that actually run on remote servers. Servers that'll never modify infrastructure, but they actually do want to read values out of your source of truth in order to find one server to talk to, or to see how many of a server exists, or so on. So you could actually script it too. So this accepts any interpolation syntax, so anything you could put in a Terraform configuration, including function calls. And the nice thing about it is that it's good, like I said, for beginners and advanced users. There's a use case for both. And it works with remote state. So if you are using remote state, your state's not even stored locally, it just downloads that state on demand, throws it away, and uses it for that period of time. So it's a really nice way to just grab values. Moving on to conditional values. One of the earliest sort of requests in Terraform was a way to have conditionals, if statements on things. And conditional values are finally an approach to that. It's not a solution, like it's not a full solution. It solves a major use case of conditionals, but doesn't solve all of them, and we don't claim it does. And so here's what they look like. They let you have conditional statements on single values of things. So in this case, we're changing the machine type of a Google instance based on what the current environment is. If we're in development, we want a small one. Otherwise, we want a standard one. Pretty simple. One of the nice things you can do with conditionals is actually turn resources on and off. So in this case, we're saying that when we're in development, we don't want any of these servers. Otherwise, we want 3. And so by setting a count to 0, it's kind of a clever way to just shut something off and not have it on for a certain run. So there is statements, and this is really just the beginning of more logic coming into Terraform. But like I said already, this solves a huge number of the use cases we were collecting for conditionals. There's a few major ones missing still, but this definitely solved a lot of real problems that we were seeing. Next one is the Terraform version requirements. It's easier to see this and then explain the use case. So the Terraform version requirement lets you put the Terraform required version directly in your configuration. So you would put this right in your TF files. And it restricts the version of Terraform that could operate in any way on those files. And so the use case for this really was we'd fix a bug with one specific part of Terraform, like a very specific, like the AWS load balancers, when they have this one parameter, now work. And so there was some known bad version of Terraform that you were running into, perhaps, with your configuration, and you don't want people to use it. Prior to this, even if all of your organization upgraded, there might be that one person still that's running the old version and accidentally recreates the buggy behavior. And so this lets you constrain it. And so you can specify multiple too. So you could say greater than 0.8, less than 0.9, and then say the known bad version for you is 083. Then you could put a comma and say not equal to 083. So it's anything between 08, 09, but specifically not 0.8.3. And you could just keep adding that along. And you could also put these inside modules too. And so when Terraform runs, it verifies that both your configuration and all the modules you're using have validated version constraints on Terraform. And when it fails, it looks like this. So even if I were to run something read-only like console, in this case, it failed, and you could see the module that caused it to fail, which is just my root configuration, the constraints that it was requesting, and the current version that I'm running. And you could see that it's just stopped it immediately. And I mentioned all this. And so in 0.8, we also introduced a couple new providers. So we introduced both a Nomad and a Vault provider. And this is sort of in an effort to integrate more of our tools together. And I'm going to talk about both here, and I'll start with the Nomad one. It's worth mentioning that 0.9 is starting to introduce, I think there's 3 resources now, but it's starting to introduce Kubernetes support as well. And there'll be more and more, we're basically adding a resource or 2 of Kubernetes every single 0.9 release currently. And so if you use Kubernetes, this is exactly applicable to you too, since the use case of Terraform and Nomad is pretty much identical to Terraform and Kubernetes. So the Nomad provider, just taking a look at it first, allows you to communicate with Nomad and register jobs. The general use case for this is that Terraform is probably setting up your infrastructure anyways and setting up the infrastructure Nomad is running on. And then as part of a scheduler, there are very often in Nomad nomenclature we call system level jobs. There's very often jobs that just run either on every machine or run to support the entire cluster that a developer isn't really actively deploying. They're just things that happen. So in this example, what I'm trying to allude to is that you may be running a monitoring agent on every machine, and you just want to schedule that because it's a fundamental requirement of your infrastructure. And so you could schedule those and initialize those. Another use case is configuration. So a lot of what we're doing with Kubernetes at first is focused on configuration, defining the templates that are available for developers and other just aspects of configuration. And so another thing is it's not expected to replace Nomad Run or the equivalent with Kubernetes. It's not expected to replace the deployment of applications on top of the scheduler. We're not trying to push Terraform as the way that you deploy all applications, even if you use a scheduler. The point is to complement those and actually set up basic jobs that you need in the infrastructure so that your developers can use features like Nomad Run right away on the cluster. Oh, sorry. I'll get that back. Okay. And then there's the Vault provider. So the Vault provider is a little bit different than a scheduler, and I'll just show you an example here. So there's a couple ways you could use the Vault provider. One is as a data source, and this lets you read secrets. So you could actually read secrets, and in this example, we're passing authentication for a run deck into the provider configuration itself. So this is a super nice way to already use a tool like Vault and grab AWS credentials and other things out of it and pass it right on in. Lets you avoid secrets directly in your configuration or as variables. The other thing is writing secrets. Maybe you get a secret as part of setting up a server. You get a key or something to that effect, and you need to write it. And then the last one is Vault policies. And so this gets into not just managing the data of a system, but also managing the metadata around it, the configuration. And so treating your Vault policies as infrastructure as code is a pretty nice way to do things because you can now do pull requests on GitHub and review just as you would any application, except it's your Vault policies. And so this is similar to also like I just said, the Kubernetes configs and stuff like that. So read and write secrets from Vault, configure policies, and you can imagine a case where Terraform just set up your new Vault cluster and it's doing the initial setup for you. So that was Terraform 0.8. Then just a few months later, Terraform 0.9 came out. So if you see like from March 15th to December 13th, that's basically like 3 months, a 3 month window where we released two really major things. And so easy to miss this stuff. And the three things I want to talk about in Terraform 0.9 are destroy provisioners, remote backends, and state locking. We'll start with destroy provisioners. To start, I'll just talk about what provisioners are before 0.9. So in 0.8 earlier, provisioners are a feature of Terraform that have existed since Terraform 0.1. They allow you to run arbitrary code locally or remotely as part of resource creation in order to set things up. So you could run a configuration management tool, you could run a shell script, and you could run it on your machine, you could run SSH and run it on the remote one, you could WinRM into a Windows machine. There's a lot of options. When a provisioner fails, Terraform marks that resource as tainted, which just means that the next time it runs, it needs to destroy it and recreate it and retry. We have to take that approach just because we don't know what a provisioner is doing. We don't know if it's safe to run the provisioner again and just retry that way. And so the most conservative option is the only option we have, which is to just destroy and recreate. And then it looks like this. So here's a resource where on creation we echo foo. And the main thing people wanted was a way to run arbitrary code as well when a resource is destroyed, to perform cleanup and things like that. So now with 0.9, you could do something like this, which looks the exact same, except we added a new field when, which describes when a provisioner runs. And the only options currently are create and destroy. But we're considering, for example, adding update and other things in there. Gives us more options for the future. But for now, you can now run something when you destroy. So using this example, we apply on creation, you can see the echo foo. And when you destroy, you see the destruction provisioner run. So all this is there. A different behavior with destroy provisioners, though, is when they fail. So when a creation provisioner fails, like I said, it taints the resource and it retries the whole thing. When a destroy provisioner fails, it cancels the actual physical destruction of the resource. Destroy provisioners run before a resource is actually destroyed. That lets you SSH into that resource if you need to perform some cleanup, exfiltrate data, something. But if it fails, we just cancel the destruction, and then we do retry it next time. But you could configure that with this onFailure parameter. So if you specify onFailure continue, then it ignores it. So here's an example where we don't. Exit 1 will obviously fail. We run it, it fails, the thing doesn't get destroyed. I could run Terraform destroy force over and over and over, the same result will happen. If I specify onFailure continue, not rocket science, just sort of completes, ignores the error, and continues. And this is nice for scenarios where you'd like to gracefully clean something up, but if you don't, it's not disaster. It'll get cleaned up eventually somehow. You have some other way. So you just say onFailure continue and let it happen. And I mentioned all this stuff. Okay, the next thing, and this is probably the biggest thing that went into, the biggest from like just a amount of change that went into 0.9 is remote backends. And remote backends are actually our replacement for remote state. And they're backwards compatible with remote state, but it's their replacement for remote state. And so understanding the motivation for remote backends is super important. And to do that, I want to talk a little bit about the issues with remote state prior to 0.9. So prior to 0.9, you would configure remote state using this remote config command. And it's a pretty awkward command. You have to specify, you'll see in the next slide, but you have to specify everything on the command line. There's no way to set things from files. There's no way to force a user to run this command. So to the second bullet point, users could, if they forgot to run remote config, could easily accidentally run Terraform against local state, which would probably be empty, and just create a complete duplicate of your infrastructure. There was a strange behavior of storing a local cache of your state in this file, which confused what you should ignore with version control, what you shouldn't, and also left some secrets in version control potentially. And then changing your remote configuration was super manual. You would have to orchestrate that very carefully across everyone using remote state. And so we wanted to solve all these problems, and our approach to that is this remote backend system. So if you look at, this is before 0.9, this is the old style, this is sort of that awkward command you would use to configure, and one of the things we were trying to address. So remote backends are something that replaces remote state, but also adds more features to it. So remote backends are the way we enable locking, we enable environments, which are another new feature in 0.9, and some other stuff. If you're, like I said, it's backwards compatible, so you're continuing to use remote state. You just generally don't get the new benefits of remote backends, such as locking. You would have to upgrade. We now allow you to configure backends from multiple places, not just the command line flags. You could use Terraform configuration. You could use an external configuration file and more. And then we also detect any configuration change for you. So we don't let you continue use Terraform when someone else may have changed the way that remote state happens. And we force new users to reinitialize. And then finally, we introduced one command to set this all up. And I'm going to talk about that a little later, but you set it all up with Terraform in it. So here's what it looks like now. You could configure it from a file. We support all the same ones we supported before, so there's like a dozen different places you could store the stuff. S3, OpenStack, Azure Storage, Terraform Enterprise, local files, console. There's a ton of stuff in there. You configure with a file. You run Terraform in it, and it sets it up. Pretty straightforward. If a new user doesn't run in it, we detect that now and then tell them to run in it and explain why. So you can see here the reason why they would do that. And if you change something, so say you have that config and we change the bucket to a new setting, we also detect that. And we'll tell, when people pull that down, we'll tell people to rerun in it there. And there's a bunch of other reasons too. And so the next thing that's useful to talk about is this Terraform init thing. But before that, actually, another important change is now there's no state stored locally at all. So if you use Terraform remote state, Terraform requests the state at the time of use, uses it only in memory, and then doesn't persist it anywhere. So that solves a major issue where that local cache existed. And a lot of people were trying to use remote state to get sensitive state information off their disks, and now it just never gets written to disk. Also makes it really clear, the official documentation stance now is that you always ignore the complete contents of the .terraform folder. We're never going to put something that should be committed to version control in there ever again. So you can just ignore it. We also focused a lot on safety. Remote state was really helpful before, but there was still a lot of different ways you could corrupt it. And by corrupt it, I mean accidentally pushing the wrong state, modifying it at the same time as somebody else, things like that. So remote backends add a bunch of different layers of safety that are new. And so one is the change detection. If a change happens, we don't let you write state anymore to the old location. Another thing is this lineage check. A lineage just makes sure that the state you're modifying is the state for your set of infrastructure resources, not a state for completely different infrastructure, and so on. There's a bunch of new features that focus on safety. And then finally, this init command. So the init command has existed since Terraform 0.1, but it did a very different thing. It used to just set up folder structure for new projects. It was very rarely used. It wasn't very useful, especially once you were past the absolute beginner stage of Terraform. And so we decided to make a change. It still does that, but now it's basically the single source of initialization. We're trying to push it as the command you run whenever you use Terraform on a new set of configuration. It's safe to run multiple times. If you don't remember if you ran it before, you could still run it and nothing changes. It's okay. But it does a bunch of things now. So in addition to initializing the backend, it also downloads modules and still does that initial folder creation if that is necessary. It's also going to be the source of more initialization stuff in the future. So, we're working on a way, for example, for providers to be loaded dynamically or versioned separately, or have third-party providers or your custom providers be able to be referenced from code, and that sort of stuff is going to all happen during the initialization process. Okay, I think this is the last thing. I'm going to talk about state locking. So state locking is a feature also in Terraform 0.9. We've always locked state in Terraform Enterprise for a very long time. It's one of the features that exists there. Terraform Enterprise still has additional locking features that Terraform doesn't have, but the fundamental aspect of locking your state to prevent concurrent writes is something we moved down into open source. And the reason really was because we considered it just a fundamental safety mechanism. There was too many cases of teams corrupting their state by overwriting each other, and so we needed a way to just prevent that. So it only works for supported backends. The supported backends, I think, currently are relatively limited. It's S3, Console, Terraform Enterprise, and that's it. So if you use a supported backend, then Terraform automatically will lock your state for any operation that may write. So not when it writes, but right at the beginning for anything that may write. If an unlock fails, if a lock fails, it just won't let you continue. That's quite simple. If an unlock fails, then we give you a lock ID to allow you to safely attempt to unlock the lock, but not unlock somebody else's lock. And so here's an example where, say, we're using console, using this new backend syntax to configure it, and we have a resource that takes a long time. We're just sleeping for 10 seconds here. So in one console, I run Terraform apply. It starts happening. You don't see anything related to locking. Like I said, it happens automatically, so it did acquire a lock here. If you're using a backend that supports locking, Terraform will never not lock it. Like it'll force locking. And in another console, if I run Terraform apply while that other one's running, you can see that it'll fail to lock the state, and it dumps a bunch of information about that, about who was trying to do it, when they initiated the lock, what version they were using at the time, all this sort of information. The important one there is also the lock ID. It's that UUID thing at the top. You could use that to attempt to unlock it, but that's pretty dangerous. So only do that if you know. Dangerous in the sense that if that lock is valid, if someone's actually making changes, that's how you could corrupt states. So you only want to unlock when you know for sure that they're done making the changes and maybe an unlock failed. But then below it, I show you that if you do a read operation like a console, we just let it on through. And in this case, we'll download the previous state or whatever is currently there and let you read it. So that sums up all the new features of Terraform 0809. You can see there's a lot of stuff. Hopefully some of it applies to you. And then the introduction to Terraform as well. A couple just call-outs I want to make are, we have a couple events coming up. We have Hashi Days New York City, May 15th. Hashi Days are a new thing we're doing this year, which are single-day technical events with open spaces attached to them. So if you want to, if you can't go to HashiConf for whatever reason, which is a multi-day event with training and so on, Hashi Days are a great way to show up and have a more affordable, shorter event. And we're trying to do these in more places. And this year we're doing two. So we're doing the one in New York City on May 15th, and we're doing one in London on June 12th. And we'll have engineers from every product team there. I'll be there. And it's just a great way to meet a lot of the more technical side of HashiCorp. With that, thank you, and I'm going to hand it off to Calvin.
Great, thanks, Mitchell. Can everyone see my slides here? Cool. So I'm Calvin, CTO and co-founder of Segment, and I'd like to share with you a little bit today about how Segment uses Terraform internally and what we've learned over the course of our journey with Terraform. Now, we've actually been using Terraform for quite a while at this point, almost 2 years to the day coming up here. And over the course of that time, our setup has evolved a lot. Just to give you some context kind of by the numbers, we've been working with Terraform for about 2 years. I looked at the repo a couple of weeks ago, and we had 25 different developers who were using Terraform to manage our infrastructure on a daily basis. It's running a couple hundred different microservices within our AWS account, and in sum total, we're managing thousands of different AWS resources, from instances to auto-scaling groups to security groups. It's all stored within Terraform. And today, I'd like to share with you just kind of two ideas that we've learned over the course of this time. First, how to write and manage what we consider to be good Terraform, and then second, a few ideas we've had for moving this beyond infrastructure. So first up, writing good Terraform. What exactly does that mean? When I think about what we've learned from the very early days, where it's very easy to get started with Terraform, where you provision some instances and almost like magic, they appear in your cloud environment. As we've grown our team and the number of people working with Terraform, there's kind of two main pieces that have stuck out as sticking points that we had to learn and understand. And those two were, first, how to manage your state, and then second, how to organize your modules so they're easy to use. So first off, managing state. As I recall from Mitchell's presentation earlier, you can think of your state as being this giant JSON file, which is tracking everything that Terraform knows about in your infrastructure. So if you make a change locally or to how your services are configured, Terraform will actually diff against your state or your remote backend, and it will come up with all of the subset of changes that need to be applied to make your desired state reflect what currently lives in production. And in our case, the way we have this set up is we actually have different states per each environment. So we have one state for development, one state for our staging environment, one state for our production environments. All of them are managed by Terraform, but none of them interact or share any of the resources together. And they're actually set up as separate files on S3. And in addition, when we were first moving to Terraform, we set up a VPC peering agreement or VPC peering connection so we could take our resources that were currently existing and seamlessly start moving them over to this production account. Now you might ask kind of what are the advantages of having individual states per environment? Couldn't I just put this all in one state and track it there? Well, the main answer is safety, per a lot of Mitchell's points earlier. And actually, there's a recent paper that came out about why safety was so important. There are some researchers who are analyzing how software engineers decide which software to actually adopt. And what they found is that pretty much regardless of the upside, even if there was an 80% chance that this tool would provide 100x improvement and really improve your efficiency, basically what they found is that developers, by and large, adopt tools that minimize the risk of doing something bad. You don't want to destroy your infrastructure. You don't want to create some sort of bad config. And so the way that we found making Terraform easy at Segment is basically making those sorts of actions hard. By default, Terraform is incredibly powerful. You can boot up thousands of pieces of infrastructure with a single command, and you can also tear them down. And so what we found is that by separating these states, we actually make safety kind of a top-level priority so that our developers can apply at will without stepping on one another's toes and without accidentally destroying core pieces of infrastructure. And in addition, not only do we have states per environment, but we also have states per service. And so what that means is that we have a set of kind of core pieces of infrastructure, things like our VPC, our networking, security groups, and auto-scaling groups. And that all lives in one state that's in a separate repo. But then additionally, we have individual services which get their own states as well. And those services actually have read-only access to that core state, and each one is applied individually. So it means that if you're a developer who's working on the app, you don't have to worry about overwriting some CDN code or destroying those resources because you're not working with the same state. And so for an example of how this works in practice, Terraform actually has this remote state resource where you can provide read-only access to some sort of state that you have hidden elsewhere. So in our case, let's say we have our core state that's stored on S3. We can say, hey, I want to create this remote state resource, which is read-only. I can never modify it. I can't tear down those resources. And then elsewhere, I can actually reference outputs or variables that are stored within that state, and I don't have to worry about accidentally modifying them or tearing them down. In practice, the way this works for us, or has worked for the past maybe a year or so, is that each individual service gets put on S3 under its own folder, and within that folder is where the state actually lives. And we'll likely be changing this up with some of the remote backends that Mitchell just talked about. So to summarize here, the state management is one of the utmost important things that you can do when planning your Terraform setup. In our case, we separate the core state from individual services, which might be changing all the time, while the core is a little bit more static. And then we actually have both states per service and per environment. And recently, we've actually decided to start ditching most of the state management ourselves by moving over to Terraform Enterprise as a way that Terraform Enterprise will just kind of handle all of these locking and safety guarantees that Mitchell talked about earlier. If you're using your own state management, I'd highly, highly recommend using S3 from the get-go. In our case, we ended up storing it locally for a while, which of course creates conflicts when two developers try to manage similar applies at the same time. So that was state management. I'd like to next talk about how we think about writing modules at Segment. And if you'll remember from what Mitchell said, modules are just a collection of resources. You can reuse them, you can pass different inputs to them. You can think of it as a higher level abstraction on top of these individual little resources that you're already creating, things like instances or load balancers. And instead, think of things more at the application level. And so the 3 points I'd like to hit today are just one, how to think about introducing variables to your modules, how to actually compose them so they're really effective, still flexible, but still powerful, and then talk a little bit about how we deal with this in practice at Segment. So the main thing that we've learned with modules over time is that you want to use variables very liberally. Since variables are the only way to configure inputs to modules, anywhere that you're using configuration, you'll want to have some sort of variable. And the kind of flip side of that is we realize that, okay, you want to have a bunch of these variables to provide good behavior, but then you also want to have good defaults so that you don't have to supply custom behavior every time, so that the developers on your team really only have to think about what inputs to supply when they want more advanced functionality. As a quick example, we have an auto-scaling rule within our services saying, hey, for these two types of scale up or scale down, I want to change in capacity by 1. Basically just adjust the number of instances that are running in my auto-scaling group. And if you're an advanced user who's maybe dealing with one of our edge servers or a CDN where you need to adjust quickly to sudden changes in load, you can actually overwrite all of these changes and scale up by more than 1 or less than 1, whatever it is that you desire. But for the average developer, this works fine, and you don't have to even think about overwriting it. And we've found that these clever defaults actually create a simple end user interface for the rest of the team, even though the defaults get written once. As a more complex example, you could imagine CPU shares for a service. We have kind of 3 cases here. One is that the developer knows, okay, I need this exact level of CPU shares. That may be the most advanced case. The second is that they need a rough resource allocation where they say, okay, this is kind of a low CPU service. I don't really need that much. Maybe it's a medium intensity service, or maybe, no, this is really intensive. Make sure I'm on an instance which has enough free CPU shares for me to use. And kind of the third case is, hey, I just don't care. Please run my service. It'll run. It's low. It doesn't really matter. And the way that we've actually done this under the hood is by combining some seemingly scary looking parts of Terraform interpolation that actually default to these pieces, where first it will take the CPU, then it does a lookup based upon this resource allocation variable to figure out whether it's low, medium, or high, and then finally it defaults the person or the developer to the low CPU shares. And while this might look a little funky to write within your Terraform setup, we've kind of found that there's a little bit of beauty in just hiding it behind a module so that the rest of the team basically doesn't even know it's there. They know they can supply the CPU flag if they want a particular count, and otherwise pass in a resource allocation. And to the entire development team, aside from the small subset of people maintaining this module, this all just kind of works. So that was variables. Let's talk about composability, which is often a little bit hard to wrap your mind around when first starting out with Terraform. Anecdotally, we found the best luck is not to start out with a large set of modules, but instead start with a few resources that you know you need, and then start combining them and gradually building these higher levels of abstraction. As a simple example, let's say we have an IAM user. This is just Amazon's means of saying, hey, I have a user for this account, they have certain abilities, and I have the ability to provision API keys for them. If you're curious in checking out the full example, you can actually check out our stack repo, which is on GitHub under segment.io stack. We have this full user there as a module that you can use and reuse, but I'd like to just walk through the pieces of it quickly here. First, we have our kind of simplified input variables. We have the name of the user and the policy that we want to create them. And this is the only interface that a developer on our team sees. They just know they want a user, and then they want some sort of policy that that user gets. Under the hood, we actually end up creating this IAM user. We pass in that name. And we also create access keys for them automatically. So we'll say, okay, we're going to output these access keys that you can use later. And then additionally, we attach the policy, which is tied together with the user that we just created. And then we supply some various outputs so we can actually use that module's outputs elsewhere. So if we want to create an IAM user, we can reference this module and then reference its outputs in places where we want to pass it into our configuration or programs. And kind of what this looks like in concert is that we take this user module, we reference the source as saying, pull this module from this GitHub repo, use that as kind of the blueprint for this code, and pull all those resources together. Then all we have to do is pass it a name and a policy. And it makes reusing pieces of Terraform really simple and really easy, and lets you get more out of the modules because you're able to change them under the hood and add functionality as you like. So another example at Segment, the idea of workers and services. We think of workers as jobs that just consume messages from a queue, while services have to actually respond to incoming requests and have a load balancer and DNS name. So internally, we keep one worker module and one service module. The worker has auto-scaling rules and a service definition, and then the service actually ends up being a superset of that, tying in a load balancer and DNS as well. And what we can do is actually have the service module just depend on the worker module. The service module is responsible for creating those extra bits, while the worker module is responsible for creating the internal pieces of the auto-scaling rules, the service definition, basically anything that a job or service needs that's running within your infrastructure. And so in practice, we end up having a single modules repository, just like Mitchell mentioned earlier. It contains all of these primitives that individual services or other parts of your Terraform setup might want to use. And then we actually have services which pull from those modules depending on what they need. So for instance, our spec service that I mentioned earlier might actually create an IAM user, a Redis, and then also tie to this service module. And if you're interested in seeing this all together in practice, you can check out the Segment AWS stack, which we open sourced. It's basically a collection of open source Terraform modules that you can use to have production ready infrastructure on AWS in under 5 minutes. It provides you with auto-scaling groups, service definitions, RDS definitions, a VPC for all of your infrastructure. Basically everything you need to kind of get an infrastructure in the box on AWS and then build your services on top of that. So as I said, it combines all of these different things. Since we're a little bit over time, I won't run through all of them here. But you can use this today just simply by referencing stack as your source. You say, hey, I want to create a stack. The environment is production. I've got my key names and my app names. And Stack will automatically create all of those resources under the hood because they're all stored within this folder. Additionally, if you want to create services for it, it's just as easy as well. You can say, hey, I want my service here. I want to pass in a particular Docker image, give it a port to listen on, and Stack will handle the rest. It will auto-scale it. It will make sure that it's running, etc. So in closing here, I'd like to leave you with a few of our thoughts of how this actually moves beyond infrastructure and combines some of the more interesting providers that Mitchell briefly discussed earlier. You might be thinking, hey, if all of our infrastructure is now applied programmatically, how else can we use this giant setup that we have? And we have a couple of use cases at Segment, the first one being alerting. We've actually started provisioning both CloudWatch metrics as well as Datadog alerts within our infrastructure. So we can actually say, hey, when a service boots up, I want to also create all sorts of alerts so that I know exactly when the load balancer is going down, when it's returning an elevated 500 error rate, when I'm seeing timeouts on my service, etc. And we can do that because it's all part of these base modules that then feed into our other alerting systems, whether it's Slack, whether it's Datadog, etc. The second actually is cost analysis, which is something that we've recently been doing a bunch of work to post up. Recently, we published this $1 million engineering problem blog post, which talked about, as part of Q4 last year, we did a very detailed cost analysis of our entire AWS setup and found that there was over $1 million in savings that we could get annually by optimizing our spend in various ways. And from the response actually on Hacker News, it really resonated because a lot of people end up having this problem. You have this kind of multi-million line item separating, okay, this instance ran for 4.2 hours, this instance ran for 3 hours, this service spun up and down at various times. It actually becomes very hard to pinpoint exactly where your biggest costs are and where you can get the most optimization. And so the way that we handled this at Segment was by adding what we call the product area to each of our service modules so that we could actually tag and figure out where we were spending the most money. And because we added this to the core module, it meant that all developers who were writing services on top of it immediately got the benefit of it once we tagged the services. We also added to our CI a lint check to make sure that, okay, every new service that comes into existence has this product area, so we can start tagging them in the future without having to do, say, like a monthly batch process where we look at everything that's not in compliance and then fix it. And the way this works on AWS is actually fairly simple. It just tags the service or the load balancer or whatever piece of infrastructure is here with this product area. And because we're using modules as a way where the product area gets passed in, we could effectively pass it to each resource under the hood, and the developer only has to change one line of code. Additionally, to actually analyze this build, then we use the Heroku AWS detailed billing setup, which was able to pipe that data into Redshift and allow us to analyze it a little more closely. So the one thought I'd like to leave you with is, where could Terraform go? And honestly, the place that I'm most interested to see is kind of in this idea of being a cloud package manager. Now, Kubernetes or Nomad and Docker provide these awesome APIs for running infrastructure yourself, but it seems to me that cloud hosted services like RDS or Redshift or Bigtable, they're really kind of here to stay just because they offload the expertise and scope of what you need to run this really large infrastructure to folks who really are experts and have gotten it down to a science how to run these services reliably. And so what I'm imagining is that every open source repo on GitHub could have this kind of Terraform folder where when you look in it, it actually provides all of the resources that you need to apply that repo in your production Kubernetes or Nomad setup. And it will also create things like RDS instances, load balancers, etc., pieces of managed infrastructure that you'd like to use. And additionally, you can imagine that because this is cross-cloud and Terraform is cross-cloud, you could actually provide support for booting it in Amazon, booting it in Google Cloud, booting it in Azure. Wherever it is that you want to run your infrastructure, Terraform can give you the ease of access to actually boot that with enough community involvement. And it could be something as simple as Terraform plan, pass it an org and a repo, followed by the AWS folder or whatever folder that you want, and Terraform could kind of handle the rest because you know that all of these resources will work together well in concert no matter what cloud you're on. And so I'm imagining kind of the future looks something more like this, where you have Kubernetes or Nomad running on top of Docker, you have your services running on top of that, but all of these pieces of managed infrastructure, whether it's queues, load balancers, databases, those are all actually managed by Terraform. And together, we're ending up building this set of cross-cloud infrastructure that is available anywhere and able to work seamlessly to the application developer. And with that, I think my time is up. So I'd like to thank you, Mitchell, and the HashiCorp team.
Okay, everyone, thank you for joining us for today's webinar, and thank you to Mitchell and Calvin for presenting. As we said at the beginning, this webinar was recorded, and we will make the recording available after processing. We will also send an email to everyone who registered for the webinar, the complete list of questions and answers after we summarize all that data. Thank you so much for joining, and have a great day.